There's a number sitting inside a NASA archive right now that scientists cannot explain. 5.113 micrometers. Say it out loud. It sounds like nothing. It sounds like a decimal point buried in a footnote nobody was ever supposed to notice, but that number is currently the most confusing thing in planetary science, and as of July 2026, it has a research team from the Paris Observatory looking at data from a dwarf planet 3.6 billion miles away and admitting, on the record, that they do not know what they are looking at. This is not a leak. This is not a conspiracy theory dressed up with a NASA logo. This is a peer-reviewed spectroscopy study, pulled straight from the James Webb Space Telescope's own instruments, and it says something that should stop you cold. There is a chemical signature sitting on the surface of Pluto that does not match a single known compound in any laboratory on Earth. Not one. Read that again. Not we think it might be. Not further study needed to confirm. They checked. They ran it against every radiative transfer model, every known gas, every known ice, every haze particle cataloged in the literature. Nothing fit. Nothing came close. And here's the part that turns a strange footnote into something you can't stop thinking about. This exact same unexplained signal at exactly 5.113 micrometers also showed up on Titan, Saturn's largest moon, a world 900 million miles closer to the sun, wrapped in a thick orange atmosphere with rivers and rain made of liquid methane. Two worlds, different distances, different temperatures, different pressures, different histories going back 4.5 billion years. And somehow, buried in the ice on both of them, there is the exact same fingerprint of something that has never been identified in the entire history of astronomy. To understand why that should unsettle you, you need to understand how scientists actually figure out what a distant world is made of. They don't send a camera and snap a photo the way you'd photograph a mountain. They break the light apart, wavelength by wavelength, and read it like a fingerprint scan. Every molecule that exists absorbs light at its own specific address in the spectrum. Water has one, methane has one, carbon dioxide has one. Astronomers have spent decades building a library of these addresses, cross-referencing thousands of known compounds, so that when a new absorption line shows up, they can usually just look it up. Case closed in minutes. Except this time, the library came back empty. When the research team, led by planetary scientist Bruno Bézard, pointed Webb's NIR spec and MIRI instruments at Titan, and then went back through archived Pluto data from May 2023, they found a dip in the light at 5.113 micrometers on Titan's surface with a depth of 6 to 7%. Then they checked Pluto, same wavelength, same signature, just 3 times wider. On a world locked in nitrogen ice at nearly minus 380 degrees Fahrenheit, hundreds of millions of miles farther from the sun than Titan, something identical was sitting there, absorbing light in exactly the same place. This is where most coverage of this story stops. A weird number, a shrug, the scientists are baffled. Headline, and everyone scrolls past. But that would be a mistake, because this discovery didn't happen in a vacuum. It landed in the middle of a much bigger unraveling, a story that has been building quietly for over a decade about a planet the public wrote off in 2006 as not even a real planet, while behind the scenes it was running some of the strangest, least understood chemistry in the entire solar system. Because here's what almost nobody outside a small circle of planetary scientists knows. Pluto's atmosphere isn't governed the way every other atmosphere in the solar system is governed. It isn't run by gas pressure the way Earth's is, or Mars's, or even Titan's in the conventional sense. According to a growing body of web-based research, Pluto's climate is run by haze, actual particles of organic soot cooked out of methane and nitrogen by faint, distant sunlight acting as the dominant thermostat for an entire world. That idea was considered close to heresy when it was first proposed back in 2017. It took years and a telescope that didn't even exist yet to prove it was real. And once scientists confirmed that Pluto's haze was doing something no other atmosphere in the solar system does, the unidentified 5.113 micrometer signal stopped looking like an isolated oddity. It started looking like it might be connected to the same chemical factory that's quietly running Pluto's entire climate system. A factory that, as of mid-2026, nobody has fully mapped, nobody has fully explained, and nobody can yet say for certain what it's actually producing. So how did we get from Pluto is a frozen dead rock to Pluto might be manufacturing a molecule humanity has never seen in less than a decade? That story starts with a spacecraft, a 9-year journey, and a flyby in 2015 that broke the textbooks the moment it happened. If you're new here, hit subscribe before we go further, because what NASA found next is the reason this mystery even exists in the first place. Rewind to July 2015. NASA's New Horizons spacecraft, after a 9.5-year, 3 billion mile journey through the dark, screamed past Pluto at over 30,000 miles per hour, giving humanity its first and only close-up look at a world we had only ever seen as a fuzzy smudge of pixels. What it sent back broke the textbooks, instantly. Pluto was not the dead, cratered, geologically frozen leftover everyone expected. It had glaciers made of nitrogen ice slowly flowing across its surface, the way glaciers flow through valleys here on Earth. It had mountains built from water ice, frozen hard as rock at those temperatures. And it had something nobody was fully prepared for. A hazy, layered atmosphere stacked in dozens of visible bands, stretching hundreds of miles into space, far thicker and far more structured than anyone had modeled. This was not the corpse of a planet. This was something active, something still changing. And that single flyby, that one brief pass, was the only direct look we would get for years. Everything that came after had to be pieced together from a distance, stitched together from theory and guesswork, waiting for better instruments to arrive. One of the scientists who studied that data the hardest was Xi Zhang, a planetary scientist who, in 2017, published something close to heresy in the small world of atmospheric science. Based on what New Horizons revealed, he proposed that Pluto's haze wasn't just a cosmetic layer sitting on top of the atmosphere. He argued it was the engine of the entire planet's climate. Not the gas, not sunlight bouncing off ice. The haze itself, tiny particles formed when weak, distant sunlight cooks methane and nitrogen into complex organic soot, was absorbing solar energy during the day and radiating it back into space as heat at night, acting as the dominant force controlling the temperature of an entire world. It was, by his own admission, a strange idea. Most planetary atmospheres are governed by gas. Pluto's, he claimed, was governed by smoke. Plenty of his peers were skeptical, but Zhang's made a prediction that could actually be tested. If the haze was doing what he thought, it should be glowing faintly in the mid-infrared, in a specific band of light too dim for any existing telescope to catch. And then he waited. For 6 years, that prediction just sat there, unprovable, because nothing on Earth or in orbit was sensitive enough to detect a signal that faint from that far away, in that exact slice of the spectrum. That changed when the James Webb Space Telescope, after years of construction delays and a launch on Christmas Day 2021, finally settled into its position nearly 1 million miles from Earth and began turning its instruments toward the moon, the outer solar system. It took time, calibration, and fierce competition for observing hours before Webb's mid-infrared instrument was finally pointed at the Pluto-Charon system. In May 2023, it captured something no instrument in human history had captured before, a high-resolution mid-infrared spectrum of Pluto, spanning nearly 5 to 27 micrometers, a window into the planet that had simply never been open to us until that moment. What it found didn't just confirm Zhang's prediction, it validated it almost exactly. The faint infrared glow was there, radiating heat precisely the way his 2017 model said it would, in a field where hypotheses often wait 20, 30, even 40 years for confirmation. If they're confirmed at all, this took 6. But this is where the story stops being a simple vindication and starts becoming something stranger. Because once Webb's data came in, tracking how Pluto's heat signature shifted across different regions as it rotated, it revealed something that hadn't been fully appreciated before. Pluto's haze wasn't just a passive layer. It was actively regulating the planet's entire energy balance, cooling it far more efficiently than gas ever could on its own. A world with barely any atmosphere at all, orbiting so far from the sun that sunlight arrives roughly 1,000 times weaker than it does here on Earth, had developed its own unique version of climate control, driven not by oxygen, not by carbon dioxide, but by organic haze particles cooked out of methane billions of miles from where that sunlight originated. One researcher on the project described it as a new kind of climate, not a variation on climates we already understand, a new kind. And Pluto wasn't rotating alone in that data. Charon was right there beside it, Pluto's enormous moon, locked in a tight gravitational embrace so close that for years, scientists couldn't even cleanly separate the thermal signals of the two bodies. Once Webb's instruments finally untangled them, something almost uncomfortable emerged. Charon has no real atmosphere of its own. It shouldn't have organic material building up on its surface in any structured way. And yet its polar regions are stained a distinct reddish color, and the data now points to why. Material is drifting off Pluto's thin atmosphere, crossing the gap between the two worlds, and settling onto Charon's poles, where it reacts and darkens over. Time. One planet, quietly bleeding its own atmosphere onto its moon. Nowhere else in the solar system does anything quite like this happen. Then, in October 2024, A separate Webb investigation into Charon's surface confirmed the presence of carbon dioxide and hydrogen peroxide chemical signatures that hint at the moon's deep origin, possibly tracing back to the same violent ancient collision that many scientists believe created the entire Pluto system in the first place. So by early 2025, the picture already looked strange enough on its own. A haze-driven climate unlike anything else observed anywhere. A moon quietly absorbing its parent planet's atmosphere and surface chemistry. And then, buried in the same archive, sitting there since 2023, was a number nobody had fully explained yet. 5.113 micrometers. Once researchers went back and looked closer, everything got recontextualized. Because if Pluto's chemistry was already this unusual, an unidentified compound sitting on its surface stopped looking like a footnote. It started looking like the missing piece of something much bigger, and that's exactly where the story turns next. So here's the actual question every planetary chemist has been quietly asking since that bizarre-led study landed in mid-2026. What if the haze that's controlling Pluto's climate is chemically linked to whatever is producing that 5.113 micrometer signature? What if the same photochemical factory, sunlight cooking methane and nitrogen into complex organics that built Pluto's climate-controlling smog, is also capable of building compounds we've simply never cataloged because no world close enough to study has ever made them before? Nobody has confirmed that link. To be clear about where the science actually stands right now, the researchers themselves have been careful. This isn't being framed as a new element or an exotic discovery of alien technology. It's an unassigned spectral feature, meaning scientists found a dip in the light, and when they checked it against every known ice, gas, and organic compound in the literature, nothing matched cleanly. They did find a short list of plausible candidates worth testing in the lab, a group of chemicals called allenes, and, if mixed with other compounds, benzene, chitin, or possibly acetylene, on Titan specifically. But candidates are not confirmations. Until something is measured in a lab under Titan-like or Pluto-like conditions and shown to absorb light at exactly this wavelength, the feature stays formally unidentified. That's the honest, less dramatic version of the story, and it's still remarkable enough to matter, because here's what can't be explained away. The absorption line on Pluto isn't some faint, questionable blip buried in noise. It showed up with a depth of 4 to 5%, roughly 3 times wider than the version detected on Titan, and it shows up consistently on the surface, not in the thin atmosphere hanging above it, which means whatever this is, it is physically sitting on the ground, embedded in ice at temperatures cold enough to freeze nitrogen solid. Something is stable, present, and measurable in one of the harshest chemical environments in the solar system, and it does not correspond to a single compound. Humanity has synthesized, sampled, or cataloged with confidence. Now think about what makes Titan and Pluto sharing this signature so strange in the first place. Titan orbits Saturn, drenched in sunlight roughly 100 times stronger than what reaches Pluto, wrapped in a thick, hazy atmosphere dense enough to support rivers, lakes, and rain made of liquid methane, an alien hydrological cycle unlike anything else in the solar system. Pluto, by contrast, sits in near total darkness, its atmosphere so thin it barely qualifies as one, its surface locked in nitrogen ice at almost minus 380 degrees Fahrenheit. If you set out to design two worlds with wildly different conditions on purpose, you'd struggle to do much better than these two. And yet, both are producing a chemical fingerprint that has never been seen before in exactly the same place in the spectrum. Either this is one of the strangest coincidences in the history of planetary science, or there's a shared chemical process, something about nitrogen, methane, and sunlight, however weak, that reliably manufactures the same unknown compound regardless of temperature, pressure, or distance from the sun. Neither possibility is small. Both are currently unanswered. And this is where the story reaches past Pluto and Titan entirely, because Xi, the scientist whose 2017 haze prediction got validated by Webb, has already pointed out what this could mean for the rest of the outer solar system. Neptune's moon Triton is icy, geologically active, and eerily similar to Pluto in composition. It likely runs on comparable chemistry. If haze-driven surface chemistry isn't a one-off Pluto anomaly, but a pattern, a mechanism that shows up wherever you get the right mix of nitrogen, methane, cold, and sunlight, then planetary scientists may need to rethink how they model atmospheres and surfaces across multiple worlds at once. Worlds separated by hundreds of millions of miles, potentially unified by the same invisible chemistry. But here's the part of this story that should genuinely sit with you a little longer. The part that stretches beyond a distant frozen world most people already mentally filed away as not even a real planet back in 2006. Before oxygen ever existed in Earth's atmosphere, more than 2 billion years ago, life already existed here. Our planet's earliest atmosphere wasn't the breathable mix we know today. It was dominated by nitrogen and hydrocarbons. chemically and structurally, similar to what's swirling above Pluto and Titan right now. Scientists studying this haze chemistry aren't just studying two dead or semi-dead worlds at the edge of the solar system. In a very real sense, they may be looking at a working physical model of the kind of atmosphere Earth itself once had, billions of years before anything with lungs ever took a breath. What most coverage of this discovery isn't fully connecting is that Pluto and Titan together might be the closest thing we have to a time machine, a preserved snapshot of the chemical conditions life first had to survive in, conditions our own. Planet destroyed the moment photosynthesis flooded the air with oxygen and rewrote the rules entirely. And if that connection holds even partially, then the unidentified molecule sitting on both surfaces stops being a curiosity for planetary chemists and becomes something with implications for one of the biggest open questions in all of science. How do the raw chemical ingredients of a dead, frozen world become the building blocks of a living one? None of this is finished. The team behind this study has already said they're working to map the feature's distribution across Titan's surface using more complete Webb data, checking whether it correlates with known geological features like the moon's massive dune fields. Laboratory experiments are underway right now in 2026, testing whether the leading candidate molecules can actually reproduce this exact spectral fingerprint under Titan and Pluto-like conditions. And the real long-term answer may not even come from Webb at all, because the real long-term answer to what this molecule actually is may not come from Webb at all. It may come from a nuclear-powered rotorcraft that hasn't even left Earth yet. NASA's Dragonfly mission is scheduled to launch in 2028 and is expected to land on Titan's surface in the mid-2030s, where it will conduct in situ studies of surface composition and chemical complexity at multiple geological sites. On board is an instrument called the Dragonfly Mass Spectrometer, and according to the research team, it should be capable of identifying at least some of the candidate molecules being considered for this 5.13 micrometer signature. There's a catch, though, and it's the kind of detail that tells you how genuinely uncertain this mystery still is. One of the leading candidates, acetylene, is relatively volatile, meaning it might not even survive the sampling process intact. And Dragonfly doesn't carry on board infrared spectroscopy capable of directly observing this exact spectral feature the way Webb does from nearly 1 million miles away. So even a flagship billion-dollar mission built specifically to walk across Titan's dunes might only partially close this case, not fully solve it. Sit with that for a second. We are talking about a discovery important enough that NASA is potentially counting on a mission arriving nearly a decade from now to help explain it. And even then, there's a real chance it walks away with more questions than answers. That's not a marketing failure or a cover-up. That's just what real, honest scientific uncertainty looks like when you strip away the headlines. Now consider how easily this discovery could have been missed entirely. Webb's observing time is one of the most fiercely contested resources in modern science. Every year, astronomers around the world submit proposals, competing for a sliver of the telescope's schedule, fighting for hours to study galaxies at the edge of the observable universe, newborn stars wrapped in dust, exoplanets that might hold water. Pluto, a dwarf planet most of the public had already mentally filed away as a settled story 2 decades ago, had to compete for attention against some of the most spectacular targets that exist. And yet, a research team willing to revisit, archive 2023 data, and dig into an underexamined slice of the spectrum between 4.9 and 5.4 micrometers, chosen specifically because it's the region least affected by haze extinction, found something nobody was even looking for. That decision, a handful of scientists deciding an old, half-forgotten world was worth another look with sharper tools, is the entire reason this mystery exists in the public record at all. And once you step back, this discovery didn't arrive as one dramatic press conference moment. It arrived the way real science almost always does, as fragments. The haze prediction in 2017, the atmospheric confirmation in 2023, the Cairn chemistry in October 2024, and now in the summer of 2026, an unidentified absorption feature stitched together from archived data, published on Archive, picked up by outlets across the science press within days of each other in early July. Nobody sat down and unveiled Pluto's secrets in one tidy announcement. The picture had to be assembled the hard way, one peer-reviewed study at a time, by researchers in France, by teams cross-referencing Titan and Pluto spectra against each other, none of whom could see the full puzzle in advance. So what actually happens? Next, right now in 2026, the team is running laboratory experiments, trying to reproduce this exact absorption using the leading candidate compounds under conditions that mimic Titan's and Pluto's surfaces. They're also working to map how the feature is distributed across Titan's disk, checking whether it lines up with visible geological structures, like the massive dune fields that stretch across the moon's equator. If it does, that correlation alone could tell scientists whether this mystery compound is something actively being produced and deposited by ongoing surface processes, or something ancient, left over from billions of years of slow photochemistry. Either answer reshapes how we think about chemistry on cold, distant worlds. And here's the honest, unresolved center of this whole story. Right now, this week, there's a documented, peer-reviewed gap in the light coming off two different worlds in our own solar system. And nobody, not the researchers who found it, not NASA, not any lab on Earth, can tell you exactly what's causing it. That's not a cover-up. It's not NASA hiding anything from you. It's something rarer and, honestly, more interesting than a conspiracy. It's the frontier of what we actually know, sitting in plain sight, published openly, waiting for someone to finish the work. Pluto was discovered in 1930. It took 85 years before a spacecraft finally got close enough to see its surface in real detail. It took until 2023 for a telescope to finally capture its atmosphere's true energy signature. And it took until 2026 for scientists to admit, on the record, that something sitting on its surface doesn't match anything in humanity's entire chemical library. Every decade, this small, distant world forces science to admit it knew less than it thought it did. Somewhere out there, 3.6 billion miles from where you're sitting right now, there's a molecule with no name, embedded in ice colder than anything on Earth. And the only honest answer anyone can give you today is that we don't know what it is yet. If this kind of deep dive breakdown is what you come here for, make sure you're subscribed, because the next update on this mystery, whether it's a lab match, a dragonfly finding, or a whole new twist, is coming. You're not going to want to miss it. Drop your own theory on what this molecule could be in the comments below. I read every single one.